Welcome to my new calculus channel. I am John Gabriel. In this video on YouTube, I would like to explain to you the concept of division and help you to understand division. Often you go throughout school and you complete your primary and high school diplomas and you obtain a degree at university, and still you never really quite understand what is division or what it actually means. Well, that's what I'm going to try and help you understand in this video. So, let's consider 1 divided by 3. Now, you'll know that using the methods that you were taught at school, you would write 1, which is the dividend there, and 3, which is the divisor here. And truly speaking, it doesn't really matter what you put up here as long as you multiply it by the divisor and subtract it from the dividend. So let's put 1 in this case here, just for the heck of it, and say that. Yes? So we could stop here, in which case we could say 1 divided by 3 is equal to 1 minus 2/3, which is 1/3, right? So it doesn't really matter what you put up here. It doesn't matter. As long as you multiply it by that value and subtract it from the dividend. And you will always get to the right answer, no matter what. Similarly, you will see that if you try the same exercise with 4 and 3, it doesn't matter what you put up here. Let's just put 1 again, no problem. And you will see again that 4 divided by 3 is equal to 1 plus this one over 3, right? In other words, 4/3. Okay. So as you can see now, in this particular case, nothing really happened. You didn't actually perform a division. All you did was this. You drew your straight horizontal line like that, and you put the 1 at the top and the 3 at the bottom. Okay. This is so because there is no division possible in algebra. There is no algebraic division possible when the numerator p is less than the denominator q. Okay, so no division can be done algebraically when p is less than q. Nothing happens here. So if you say p divided by q, while this can be done geometrically, it can't be done algebraically. So we simply state the division as p over q. This is not something that still has to be divided. It has been divided. It is a number. P over q is a number, just as 1/3 is a number, or 4/3 is a number. Now, where do we get this process of division from? Well, if you look at this sign here, it's called an obelus. Okay, this is called an obelus. And the way we do obelus division is, as I've just explained in these 2 examples. So we take a particular number and we subtract the divisor each time until we have a remainder that is less than the divisor. Okay, less than the divisor in this case here. So 1 is less than 3, then we stop. In other words, in the case of a proper fraction, no division takes place algebraically. So an obelus is based on the Euclidean algorithm. And this here is the Euclidean algorithm we've been using. And we can actually write down the Euclidean algorithm as follows. We can say if a is the number that we're dividing by d, then we simply say a is equal to d plus some remainder. Okay, and then remainder is equal to d plus another remainder, and so on until we get to a point where the remainder is less than the divisor. So this basically goes up to Rn, and here we'll have Rn plus 1. Then we sum up the number of times that we had to do this process, and that total there is going to be the sum of the partial quotients. Okay, these here, the ones in front here, are the sum of the partial quotients. So if we sum these up here, that will give us S. Now I'll do an example for you so that you can understand what this means here, okay? So let's suppose that we're going to divide 21 by 5. Alright, so we'll subtract 1 5, and the remainder is 16, yes? Then we'll subtract another 5, and the remainder will be 11. And again we'll subtract another 5, and the remainder will be 6. And we'll subtract another 5, and the remainder will be 1. And you can see here that these partial quotients give you 4, right? And of course there's 1 left, 1 divided by 5, so it's 4 plus 1 divided by 5. The stopping condition occurs when Rn plus 1 is less than D, right? And in this case here, this here is less than D. Can you see all these here are greater than 5, but this one here is less than 5. So we've reached the stopping condition, and that is the answer. Does that make sense? Okay, so now if we had to write something like this, 1 is equal to 0.3 plus 1, this really implies that 1 divided by 3 is just 1/3, because nothing happens in this algorithm, right? Here's the Euclidean algorithm. Nothing happens because 1 is less than 3, okay? 1 is less than 3. So nothing happens. We just put the 1 on top of the vinculum and the 3 on the bottom of the vinculum. Geometrically it's possible to divide a line, and I can show you how that's done. Well, suppose this was the line that we were going to find a third of, okay? We want to find a third of that line. Well, we don't even have to divide this line segment here. All we need to do is create another line segment which contains the length of these 3 line segments. And now we know that number is 1 and this number is 3, and hence we have the idea of 1/3, right? So we have 1 and 3, and that gives us 1/3. Okay, so the next thing I'd like to talk about are the conversions to radix systems, whereby we take a proper fraction and we convert it to a certain base. So let's look at an example of that. Suppose I ask you, what are we doing when we write 1/4 equals to 0.25? What would you say we're doing? Well, we are attempting, if we don't have this here and you're asked to write it in base 10, then you're attempting to find an equivalent fraction in base 10 whose denominator is an integral power of 10. Okay, so how does that work? So in other words, what you have is something like this, okay? And you need to multiply it by something so that you have an integral power of 10 here and a number up here. So how can you do that? Well, what if you multiplied by 25 over 25? Right, then in this case here you have 100, and in this case you have 25, and that's the same as 25 over 100, which is an integral power of 10. It's 10 squared, which is equal to 0.25, and that makes sense. And now notice that we didn't perform any division here, okay? We simply found the number which multiplied by this would give us the equivalent fraction in base 10 with an integral power of 10 in the denominator. So no division is taking place. It's not possible to do this with 1/3. Why? Because 10 does not contain all the prime factors of 3. Okay, there is no number here that when we multiply it by 3 will give us 10 to an integral power. Okay, there is no such number. So really what we're looking at is 3 times k is equal to 10, let's say, to any integer power, 1, 2, 3, 4, 5, etc. There is no k such that when we take this product, it will give us any one of these integral powers. Therefore, 1/3 cannot be expressed exactly in base 10, or measured exactly in base 10. Now, we can use algorithms that include division to find an equivalent fraction, which might make the process a lot easier. This process of converting a proper fraction into a radix representation. For example, we could have said 1/4 times 10 over 10, right? And then that would give us 10/4 times 1 over 10, which is the same as 2 plus a half times 1 over 10, which gives us 2 times 1 over 10 plus a half times 10 over 100, which gives us 2 times 1 over 10 plus 10 over 2 times 1 over 100, and we finally end up with an equivalent fraction of this form, right? In other words, we have 2/10 plus 5/100, which is the same as 25/100, which is 1/4, right? Or 0.25. 0.25. Okay, so that's another way of doing it, and you can use this approach to find an equivalent fraction in any base, provided it exists. And when I say provided it exists, the base must contain all the prime factors of the function, of the denominator that you're dividing by. Otherwise, all you have is an approximation in the base concerned. Okay, so for example, if you try to do this with base 3, all you end up with is something like this, and that that does not equal to 1/3. Okay, the limit of this is equal to 1/3, but that's an entirely different thing, and it's not a good idea to define the limit of this sum as being equal to the actual sum, and that's what Euler did when he said S is equal to lim of S, where this is S. Okay, so what is division? Let's take a look at what is division. Let's clear this board here. Yep. Okay, if we look at the process of division, it's a form of measurement. Okay, so division is a form of measurement. Form of measurement. Okay, so now what we have is a divisor on this side of the bracket, a dividend, and a quotient, and if need be a remainder, if there is a remainder. And the divisor can be any linear combination, and so can the quotient be any linear combination, and so can the dividend. They can be any linear combination that you wish. If we say 5 divides 10, that vertical line means divides. Then what that means is that 5 measures 10 exactly. Okay, in other words, it goes into 10 twice or 2 times. So we know that 5 divides 10. And we would write 5 does not divide 6. Why? Because there's a remainder of 1, isn't there? So what this really means here is that 10 divided by 5 is equal to 2, remainder 0. And you can contrast this with, let's say, 11 divided by 5, which is equal to 2, remainder 1. Clearly, 5 does not measure 11 because there is a remainder. In order to say that 5 measures 11, the remainder must be 0. Okay? So, if one number divides another number without a remainder, or a 0 remainder, it measures it exactly, doesn't it? So, while pi is an incommensurable magnitude, so pi is an incommensurable magnitude. It's not a number, it's an incommensurable magnitude. Okay, we can say that pi divides k pi. Okay, in other words, pi divides k pi k times. So this concept of measurement is not only restricted to integers, as we see in these examples here, but also to incommensurable magnitudes. Yes? Alright, so that's pretty good. Now, for the last part of this video, I'd like to take a look at something called the greatest common divisor. And that also stems from Euclid's algorithm, which we've been discussing here. But before I do that, I'd like to give you an example of the process that I've just discussed on this page here. So I'd like to give an example of how all this works. Why don't we just move this to the side? Okay, like so. And let's do an example. So we could, suppose we wanted to divide 20 by 5, right? 20 by 5. We could rewrite that as 3 plus 2, which is a linear combination of 5, divided by any linear combination of 20. I just chose those numbers randomly, okay? So they didn't have to be 10 plus 4 plus 6. It doesn't matter. Any linear combination will do. And so now we can say, 3 goes into 10 5 times. It doesn't really, but it doesn't really matter what you put up here. Okay, isn't that amazing? It doesn't matter what you put up here because you're going to multiply it by both these partial divisors. These are partial divisors, and then subtract those from the entire dividend. So if you do that, then you have this, right? And if you subtract these from this line here, what you're going to get is minus 5, right? Okay, and again you can say, oh well, let's say 3 goes into minus 5 minus 2. I'm just picking these numbers, but it doesn't matter which numbers you pick. Obviously, when you want to do the algorithm in a little more structured way, you will arrive at the answer sooner. And I'm just doing this to show you that it doesn't matter how you do it, but it will give you an idea of how it works. And so you can say this is the same as minus 6 minus 4, right? With a remainder of 5, and you can say, alright, well this is 5, so 5 goes into 5 once, and we're pretty much done. We put 1 here, 5 here, and 0 here. Okay, so how does this relate to the Euclidean algorithm? Okay, let's see how. So if you write the individual steps, it will be 20, which is the entire divisor, and 5 is the divisor, which is 3 plus 2, and the first one we used was 5, so it will be 5 times 5. The first partial quotient was 5, so it will be 5 times 5 minus 5, right? Because that was the remainder, right? These here in this column will be these will be the dividends, okay? The dividends. And these here will be the partial quotients. And these here will be the remainders. Okay, so the next one that we did here after the 5 was the minus 2, and that would correspond to the dividend minus 5, and we'd have minus 2 times 5 plus 5, right? And then of course the last one was 1, so then we'd have 5, which is 1 times 5 plus 0. So as you can see, this keeps moving here, this moves here, and so on, right? And naturally these quotients, partial quotients, correspond to these, don't they? And 1 to that, so that if you say 5 minus 2 plus 1, what does it give you? It gives you 4, and that's exactly right, because 20 divided by 5 is 4. Okay? So that just gives you an idea of the concept or the process of division as conceived by Euclid through the Euclidean algorithm and perpetuated in the obelus operation. So the obelus operation actually does all these things, but only when the divisor is less than the dividend, okay? The divisor is less than the dividend. If the divisor is greater than the dividend, nothing happens, except that we just put the numerator on the top of the obelus and the denominator on the bottom. So if we have, let's say, 3 divided by 7, then all we do is put the 3 there and the 7 there, because algebraic division is not possible. Only geometric division is possible. In other words, you can take any line you like and divide it into exactly n lengths, just using a compass and a straight edge. Okay, so now that is really all I want to discuss in terms of division, with one more concept, the greatest common divisor. So let's go back to this slide, or let's go to that slide and clear this out. Okay, and so in this one here, let's discuss the greatest common divisor. This is an algorithm derived directly from the Euclidean algorithm, and what it says is, let's just do this first. Let's let B equal to Q times D, yes, and C equal to R times D, right? And then write N is equal to B plus C. In which case, if we do this, we know that D divides B and D divides C, doesn't it? But if D divides B and C, it must also divide N, right? So this implies that D divides N. Okay, let's see an example. Take 130 and let's take 91 and find the highest common divisor. So, well, 91 is the highest value. In this case, it only goes one time into 130, doesn't it? And the remainder is 39. Okay, so now the next step would be to find the greatest common divisor of these, because we know if we find the greatest common divisor of these, then by this principle here, we'll be able to just percolate our way back up again and find the common divisor that we had, which will also divide 130. So we'll say 91 and 39, and we know that it only goes into 91 two times, doesn't it? With a remainder of 13. Okay, so in this case, we can continue the process and say that 39 divides into 13 three times. 3 times 13. 13 divides into 39 three times exactly, and there is 0 remainder. So there must always be a 0 remainder in this process. And once we get to the 0 remainder, that is the stopping condition. You will see that if you look at this process here, you will see that 13 divides both 13 and 39, right? And again it divides 13 and 39. And of course we know that if it divides both 13 and 39, then it's going to divide 91 as well, yes? Because it divides 13 and 39. So we percolate our way up again and we find, this is the greatest common divisor. Okay, the one that we have right at the end with the zero remainder is the greatest common divisor because it will go into every single one of these. Right? Does that make sense? I mean, you could just basically take 91 and add 13 to it, or 39, and you'll get 130, right? So it divides 91 and it divides 39, and so all the divisor column and all the remainder column will be divisors of 13 will divide all of those except for 0. Okay, well, in a sense 13 also divides 0 because 0 divided by anything is 0. The divisor in the row with 0 remainder will be the quotient, or the greatest common denominator, because every time we move from one row to the next we use the highest possible divisor. Okay, so every time we move from this row to this row and this row to this row, we use the highest possible divisor. I wouldn't have used 39 here in the first row because it's not the highest value that I can divide, right? Okay, and the two numbers in this case here are 130 and 91, and their greatest common divisor is 13. And this, once again, is based on Euclid's algorithm, which is the basis of the obelus and the greatest common divisor, and also the process of addition, which we saw in the other slide, okay, where we did all this process here, and in the very first slide. And so this is all I wanted to discuss in this video, but there is a lot more that I can tell you about these facts and this particular topic, and I'll try to discuss it in another YouTube video, time permitting. This is the New Calculus channel. I'm John Gabriel.